So last time we were talking about enthalpy. I want to make sure we differentiate between enthalpy and entropy. So enthalpy has to do with potential energy. It has to do with stability. If my molecules are stable because they have complete noble gas configurations and zero formal charge, and there's no torsional strain or angle strain or other kinds of steric hindrance or repulsion, and the electrons are arranged in a way where they can form nice strong attractions to the nuclei, that's a stable substance. It's low in potential energy, and it would have low quantity of enthalpy. So if you have a reaction where there's a change occurring, we can judge based on how stable the products are versus the reactants whether the enthalpy will be going up or down, and whether or not the system has to absorb energy from the surroundings in order to experience an increase in potential energy or enthalpy versus releasing energy into the surroundings if there's a decrease in enthalpy or potential energy. And that determines whether it's exothermic or endothermic, right? The thermic refers to the heat, which is what the H stands for, and the enthalpy symbol. And so if I'm looking at a change in heat from the point of view of the system, I'm looking at the system either releasing energy into the surroundings or absorbing energy from the surroundings. And since energy can't be created or destroyed, I know the quantity of energy changed for the system will be equal but opposite in sign to the quantity of energy changed for the surroundings. So enthalpy is not the end-all be-all when we're looking at whether a reaction will favor products or reactants, though. We also have to look at entropy. And we know that because there are many reactions that normally would not happen if enthalpy were the only factor. Right? If I have a reaction where the reactants are more stable than the products, why would it ever form more products than reactants when it reaches equilibrium? You would think it wouldn't. But there are examples where whatever the products are, even though they're higher in potential energy and have more potential to react than the reactants, they're less stable. There are instances where I'll end up with an equilibrium that produces more of an unstable substance than I have of the more stable substance. And that is because of entropy. So we have to also understand how entropy affects reactions. So that's what the first part of today's content is about. So when you're thinking of entropy, which is technically just S, the delta is when you're experiencing a change in entropy. The entropy of a sample or system has to do with how much disorder or randomness or freedom, or I like to think of it as variety, how much variety there is for the individual molecules. Does every molecule look the same, or is there variety? Is every molecule moving in the same way, or is there variety? Are some moving fast and some slow? Are some vibrating in different ways from others? Are some molecules rotating around all their bonds and other molecules maybe can't because they formed rings or double bonds that can't rotate? So the more variety there is in the ways that the particles can be positioned in space, as well as the ways that the particles are moving, the more entropy you have. And entropy is favored by the universe. Favored by the universe. So generally a system will produce products if the products have more entropy than the reactants, sometimes even if the products are less stable than the reactants. So those two factors sometimes go hand in hand, sometimes they don't. And so we want to understand both factors and how they play off of one another so we can predict, if we do a reaction, whether we'll actually get products. Right? I don't want to waste time running a reaction in the lab if I know, based on the enthalpy and entropy, that the reaction is only going to favor the reactants and I'm only going to get a tiny bit of products or maybe virtually no products forming in that process. So we want to be able to look at some examples and analyze how entropy works for specific examples. We were saying that the more variety there is in molecules positioning in space, and the more variety there is in the ways that they're vibrating and rotating and flying through space, the more entropy there is. So if I give you two different molecules, you'd want to look at all the different ways they can vibrate, all the different ways they can rotate, and all the different ways they can move through space. So sometimes molecules can vibrate in a greater variety of ways, and that usually depends on the number of atoms. So if I'm comparing, say, this molecule here that has 1, 2, 3, 4, 5, 6 carbons versus one that has 8 carbons, the one with more carbons will have more entropy. If it's just a straight up comparison between molecules, well, the more atoms I add, I can rotate around every single one of these carbon bonds, and I can vibrate around each individual sigma bond. Is going to vibrate where the bond will get longer, so the distance between the carbon atoms is constantly being stretched and then being compressed. It's just like a spring, stretching and compressing over and over again. So that vibration of the bonds, there's also vibration of the bonds based on the angles bending instead of just the bonds stretching. Right, so we know typically a carbon will have 109-degree angles, but there's motion, there's kinetic energy in the system. So sometimes this angle will get smaller, and then sometimes it will stretch and get larger. So there's a bending vibration that can occur, there's stretching vibrations that can occur, and the more atoms there are in my molecule, the more different possible ways they can vibrate. So the more variety there will be in the molecule's vibrational states. Rotational states, we're talking about the number of bonds. So sigma bonds rotating, or the molecule could be flipped over like a pancake. So that isn't really going to make a difference between one molecule and another, because whichever molecule I have, they both can flip over. So they both have rotational variety in the ways that they're tumbling and flipping in space. But the more the sigma bonds can rotate, the more variety there will be as well. So if I have a chain, whether it's branched or not, if there's no ring or double bonds, every one of these carbon bonds can rotate. That creates more variety. If I have a ring, or if I had a situation where I had a lot of double bonds, those would constrain, because, as we said last time, a double bond can't rotate because the p orbitals have to stay aligned side by side, and that requires the carbon sigma bond not to rotate at all. So if we're looking at entropy in terms of rotational variety, we understand that chains that don't have restrictions to their vibration or their rotations in the form of double bonds or rings are going to have more entropy. What determines the variety of the translational motion? That's determined mostly by the state of matter and in part the temperature, and the temperature actually affects all three of these. So when it comes to temperature, we know temperature represents the average amount of motion. So if I increase the temperature, each individual molecule is going to have more motion. So at a low temperature, this bond might vibrate a little bit. Some of these other bonds might not vibrate very much. If I have a higher temperature, it means I'm broadening the distribution of motion. So at a high temperature, there's still some molecules that only vibrate a little bit, but there's some that vibrate a lot more. So I get more variety as the temperature increases. And obviously the state of matter has a big impact on the translational motion. Translational motion is particles like flying through space. So clearly in a solid, they'd be packed together and they wouldn't be flying through space. Their intermolecular forces would be holding them in position. So there'd be very little translational motion at all, virtually zero, and there'd be no variety resulting from that translational motion either. So in a liquid, the particles are attracted, but they can still slide around past one another, so there's some translational motion and there's some variety. But then obviously in a gas, the particles are separated and they're all flying through space independently at high speeds. So there's much more translational variety if my molecules are moving around than if they're just kind of sitting still and only vibrating a little bit. So we want to make sure, this is all review from Gen Chem 2 for the most part. The state of matter has a big impact on the entropy as well as the structure of the molecule and the variety in the ways it can move around based on that structure. So here's an example. Just want to analyze this simple example and think about the entropy change that might be occurring and the enthalpy change that might be occurring. So here I've got a gas. It's trapped in this vessel, and this opening here is closed. So there's no way for the gas to get into this vacuum. So at this point, all the molecules are stuck in one specific volume or amount of space. So if then I open that valve and allow the gas to pass back and forth, now the particles can move throughout here. So is there a change in enthalpy? No. No change in enthalpy because there's no change in the stability of the molecules as they're just bouncing around. There's no additional attractions or repulsions that form. In a gas specifically, there's no intermolecular forces that are significant that I have to break in order for this gas to spread out. So the gas spreading out from one container to another does not involve anything happening to the enthalpy. The change in enthalpy is zero. There's no difference between the initial state versus the final state in terms of which is more stable or which has stronger attractions or more repulsion. There's no change in the attractions or repulsions there at all. But when we look at the entropy, we do see a difference, right? If all my molecules are stuck on one side, there's only so many positions in space that they can occupy within this volume. And there's only so many ways that they can be flying through space or moving within this volume. As soon as I open up the valve and now they have access to the whole area, the possible translational distributions increases with increasing volume. There's more ways the molecules can be positioned because now there's a greater volume that they're spread out in. And there's more ways that they can be moving. It's not just that they're limited to flying through space over here. They can fly through space over here and over here. And so there's more variety when I increase the volume for a gas. So if there's no change in enthalpy, but the change in entropy is positive because it's increasing, or there's more entropy in the final state and less entropy in the initial state, and if I do the change in entropy, delta always means change, that would be the final minus the initial, I'd have a larger value minus a smaller value, and that's how I get a positive number there. So anytime the entropy is going up, if there's no change in enthalpy, I know that's going to happen spontaneously, right? We know that from experience. If I have a vacuum and I expose a gas, the gas will immediately fill that vacuum. And that's because of the entropy increase. In the universe in general, there's a tendency for entropy to go up. And this particular example confirms that, or at least is in line with it. So we want to, if we want to determine whether a process is spontaneous, meaning it's going to happen in the forward direction, and when it reaches equilibrium, so spontaneous means at equilibrium, actually, let me change that. So if we're talking about spontaneous under standard conditions, that would mean at equilibrium we have more products than reactants. Spontaneous at the moment means that whatever the reactants are, they're being converted into products at a rate that's faster than the reverse reaction. So if we want to know whether something's spontaneous, that depends on the current concentrations, it depends on the stability of the product versus the reactant, and it depends on how much entropy there is on the product side versus entropy on the reactant side. So we can kind of simplify this a little bit by just looking at the entropy change. And the way that works is, if I can show that the total entropy, including both the system and the surroundings, is going up, then I know the process is spontaneous. If I determine that the total entropy is going down as the process occurs, that means it's non-spontaneous, which means specifically that it's currently occurring in the reverse direction, more than it's occurring in the forward direction. So if we looked at the expansion of the gas on the previous slide, we said the entropy change for the system was positive because there's more entropy when the gas can spread out, more variety in the ways the molecules can be moving around and positioned in space. What about the entropy change for the surroundings? Well, the entropy change for the surroundings is going to depend on the temperature change in the surroundings. The system is always defined as the particles that may be breaking or forming attractions. So you shouldn't be breaking or forming attractions in the surroundings. There shouldn't be any change in the structure of the molecules or the state of matter, probably in the surroundings. The only thing that's usually happening in the surroundings is the temperature might be going up or down, and that would depend on the sign for delta H. So if the system releases energy, the surrounding temperature will go up, and that will increase the entropy in the surroundings. Because if there's more temperature, there's more variety in the way the particles are moving around. If the system is absorbing energy from the surroundings, then the temperature of the surroundings will go down and the entropy of the surroundings will decrease. So in the example of the expansion of the gas, though, we said that delta H for the system was 0. There's no attractions breaking or forming, no change in the structure or attractions or repulsions, so there's no change in stability. And that means no energy is exchanged with the surrounding, and so the temperature of the surroundings should not change, and the entropy change in the surroundings would be 0. So if between the two of those, I can conclude that the sum of those values, 0 plus a positive number, is positive, that tells me that the process we're talking about is spontaneous. I already knew the process is spontaneous because I know a gas will expand into a vacuum, but this is just a confirmation for why that is. And we can apply this analysis to a variety of instances where it's not easy to predict whether the process will actually occur or not. We have to look at the entropy change for the system, which is the reaction or process that is going to involve breaking or forming attractions. And we have to look at the entropy change for the surroundings, which is usually the solvent or the container or the room, and technically also includes the rest of the universe. And that will usually only experience a change in temperature. But we can tell if the temperature goes up, there's going to be more entropy because there's more variety in the way the particles are moving around. So let's look at a more complicated example than just a gas expanding. So a lot of times, if I'm doing a chemical reaction, it might involve breaking a bond. And maybe the electrons both move over here because maybe element B can stabilize that lone pair. Maybe the electrons are more stable around its nucleus than they would even be shared between the two. There may be instances of that. Or maybe the reactants are actually more stable and the products are unstable. Maybe the electrons would be more stable on a cloud surrounding both nuclei versus a cloud just on one atom. Either way, the entropy should be going up. because here, when my atoms are stuck together through bonding, they always go hand in hand. I can't break one away from the other if they're part of the same molecule. So that means this acts as one particle, or 1 mole of particles. And if there's only 1 mole, that's only so many particles. So in a box with only a few particles, maybe I have 6 of these things, there's only so many ways they can be moving through space and bouncing around. There's only so much variety when I only have a few particles. So if that bond breaks and now I've got twice as many independent particles from what I started with, instead of 6, now I've got more. There's just a lot more variety now because each one is moving around independently. There's just more chaos when there's more particles in the system to move around. So this would be an increase in entropy for the system when this occurs. The change in entropy for the surroundings is going to depend on delta H. It's going to have it won't be equal, but it'll be proportional to the opposite sign for delta H. And so, for example, if the reaction is exothermic and it releases energy, and delta H is negative, a negative times a negative, that's going to give me a positive entropy change for the surroundings, right? If the reaction loses energy, the surroundings gains that energy. And it also goes up in entropy, even though energy and entropy aren't the same. If the energy that the system loses goes into the surroundings and gets converted into kinetic energy for the surroundings, the particles in the surroundings will be moving more, and that will increase the variety in the ways that they're moving around as well. So increasing the moles for the system causes an entropy increase for the system. Also, if I break open a ring and now have a chain, as we were saying before, there's a lot more ways that the single bonds can rotate all the way around 360 degrees versus the ring where the rotation is limited from flipping from one chair to another. So if I allow the structure to gain more freedom or variety in the way that the bonds can rotate, that's also going to be an increase in entropy for the system. So you want to think about how the motion or positioning of the particles changes when the reaction occurs. That's how you determine delta S for the system. Delta S for the surroundings depends on delta H for the system. Indirectly, right? So as we said, if delta H for the system goes down, because it's a system, it's losing energy, the surroundings picks up that energy and converts it into kinetic energy, which causes more variety for the motion of the particles when there's more movement, and vice versa. So you want to be able to correlate those two with one another and recognize that they're shifting in opposite directions. All right, so how can we combine this together to look at spontaneity? So let's imagine that these reactions are exothermic. So let's say somehow they're more stable in the product side than the reactant side, and we could say that for both these examples. So we're just looking at this first condition here. So if delta H is negative, that means the potential energy of the products is lower than the reactants. The reactants are unstable, and when they produce the products, energy will be released into the surroundings. So the temperature in the surroundings will increase, and the entropy in the surroundings will increase. So anytime a process is exothermic, that's generally favored to produce products because that causes the entropy of the surroundings to go up. And in both of these instances, the entropy for the system is also going up because I'm increasing the number of particles. There's more variety in the ways they can be positioned and moved around. Or the entropy for this reaction is also going up for the system because I'm increasing the variety in the ways the bonds can rotate. If I open up that ring and prevent the ring from constraining rotation, So if I have a combination of delta H for the system that's negative and delta S for the system that's positive, that's always going to be a product favored test, because the entropy of the system goes up and the entropy of the surroundings goes up if the enthalpy of the system is going down. Enthalpy lost, energy goes into the surroundings, temperature of the surroundings goes up, and so the variety of motion in the particles in the surroundings goes up. And so if the system has a positive change in energy and the surroundings, and I add those together, I'm going to get a total increase in entropy for the universe, and that being positive is what causes the process to occur spontaneously. In either of these scenarios, if I have an endothermic reaction where delta H is positive, then I have the opposite situation going on in regards to the surroundings. So if delta H is positive for the system, that would imply that if I look at the potential energy, the products are less stable than the reactants, and the difference in enthalpy being a positive change for the system, I must be absorbing that energy from the surroundings. So that's when the temperature decreases in the surroundings, because some of that energy has to be now in the form of potential energy for the system in order to make the reactants into the products. So if the temperature in the surroundings goes down, the entropy change for the surroundings is negative. If the temperature goes down, there's less ways the particles are moving around and vibrating, and less variety in the motion, and so the entropy goes down. So if the entropy for the surroundings goes down, but I still have an increase in entropy for the system, because I'm still increasing the number of particles, creating more variety, or increasing the rotational options, creating more variety, that's going to give me these two factors in competition, and it will depend on which is larger. So if it's just slightly endothermic, and the amount of energy absorbed is small, then the entropy change in the surroundings will be small. And as long as the entropy change in the system is larger than that, when I add that, I'll still get a positive overall, and the process will still be product moving toward the products in a spontaneous way. But if it's highly endothermic, and the quantity here is a large number, and the amount of energy that has to be absorbed from the surroundings is very large, then the temperature in the surroundings will go down a lot. And the entropy change will be very negative. Because if the temperature goes way down, then there's very little variety in the motion of the particles, right? If everything is really cold, like close to absolute zero, and there's barely any vibration, that's not giving you much variety. Every molecule looks like the neighbors because they're all just barely moving. So if I have very little entropy in the surroundings, after all this energy is brought into the system, and this ends up being a very large negative value, well, then I'd end up with a negative overall. And that would mean that it's not spontaneously producing products, but rather it would be spontaneously producing reactants, or that this reaction is going to give me mostly reactants in that scenario. So I really have to look at whether it's endothermic or exothermic here, as well as looking at the exact particles that are involved to see if after the reaction there's more particles or more freedom for the particles. I really have to look at the entropy change for both the system and the surroundings by looking at the enthalpy change for the system as well. So here's a scenario. We're just looking at rearranging the equation here. So if we're interested in delta S for the system, we said that can be measured or estimated. Typically, we'd be estimating that in this class. We're not doing a lot of quantitative calculations with that. That was more Gen Chem 2 stuff. So we're estimating it based on the number of moles, whether or not you've got a ring structure, whether or not there's a change in the state of matter. If a gas is converting into a solid, there's going to be much less entropy in the solid, or vice versa. as we said, the change in entropy for the surroundings depends on whether or not the system is causing a temperature increase or decrease in the surroundings by releasing or absorbing energy from the surroundings. And so this is the quantitative relationship between the enthalpy change in the system and the entropy change in the surroundings. Right? If the enthalpy is negative because it's releasing energy into the surroundings, this negative sign here, negative times a negative, gives me a positive value for the entropy change. And that's what we said, right? If the system's releasing energy into the surroundings, the temperature and variety in the surroundings goes up, or is positive, a positive change. So what I can do with this mathematically is to take this formula, since I know that entropy change in the surroundings equals negative H times temperature, I can substitute this in, in for the surroundings, and then I get this formula, right? So we're just changing delta S surroundings and plugging in negative delta H system over temperature for delta S surroundings, since those two are equal. And that gives me this formula. And if I rearrange that formula a little bit, I get a slightly different form. And then if I define the temperature times the total change in entropy, or actually negative temperature times total change in entropy, that gives me a new term that you should be very familiar with from General Chemistry 2, which is the Gibbs free energy. And when we did Gen Chem 2, we said delta G is a great way to determine if a process is spontaneous or not. The reason that's true is because delta S total is really the ultimate way of determining whether a process is spontaneous or not. If I get a positive change in entropy overall, meaning that the entropy of the universe is increasing, because of this negative sign here, I'll get a negative value for delta G. So a negative value for delta G or a positive value for delta S total, those two things mean the same thing. And those two things mean that the process is product directioned, or moving toward the products, or spontaneous. That means that when it reaches equilibrium, I'll have more products than reactants. So if I don't want to actually calculate what's going on in the surroundings, plugging in this for delta S surroundings allows me to express everything in terms of the system. And that's why this formula for delta G is nice and convenient. It puts everything in terms of the system, and I can look at the signs here for whether the process is increasing in variety or decreasing, or whether the process is increasing in potential energy or decreasing. And I can look at the signs there and then say something about whether this process should actually produce products in a significant quantity or not. And that's really what we're trying to get at here. We want to know, do these reactions produce a lot of products or not? So let's look at an example and see if we can figure out the signs for all of these terms. So here's an example. I've got this molecule here and this molecule here. So I've got 2 moles of reactants, and they're coming together to produce 1 mole. So what's the sign for delta S for the system? It's going to be negative. There's more variety when these things are apart because there's more particles that can move around independently in a greater variety of ways. If I join them together, especially forming a ring where now the rotation is limited, there's going to be a lot less variety on the product side, so the variety is decreasing as this reaction occurs. So the sign for delta S for the system is negative in this reaction. If I did the reverse reaction where the ring with the double bond breaks up to produce these more free molecules that can bounce around independently and rotate more, at least there's a single bond here that can rotate all the way around, that would have a value for delta S for the system that's positive because there's an increase in entropy. All right, so if it's written this way, though, we're looking at a decrease in entropy, so we've got that part answered. What about the sign for delta S? Well, like we did on yesterday's quiz, we can determine whether the products or reactants are more stable usually by comparing the number of pi bonds versus the number of sigma bonds. So over here, I've got a total of 1, 2, 3, 4 sigma bonds and 1, 2, 3 pi bonds. Over here, obviously we're not including the CH bonds. None of those are breaking. I mean, we could do that analysis and show that there's no CH bonds breaking. That would be important. But if there's the same number of CH sigma bonds on both sides, we can cancel that out. So between the carbons, I've got 1, 2, 3, 4, 5, 6 sigma bonds and 1 pi bond. So this particular reaction on net converts 2 of the 3 pi bonds into sigma bonds, because the sigma bond number is increasing by 2 and the pi bond number is decreasing by 2. So if I'm converting pi bonds into sigma, and these are less stable due to the electron density not being as close to the nucleus as they would be in a sigma bond, and the sigma bonds are more stable, then we're looking at a situation where we're going from a high potential energy on the reactant side to a lower potential energy on the product side. And so to get from a high to a low potential energy on net, there's a decrease in enthalpy or potential energy, and that's negative. So the sign for delta H for the system is negative. So then what's the sign for delta S for surroundings? Well, once I know the sign for delta H for the system, I can then recognize that delta S for the surroundings will have the opposite sign. And that's always going to be true, because if the system is releasing energy, the surroundings temperature will go up, and the amount of variety in the motion of the particles will correspond with the temperature. So we know that. So then what's the sign for delta G? Well, to get the sign for delta G, we've got to look at this formula. We've got a negative value here, and we're adding to that a negative times a negative, which is a positive. So when I add a negative number to a positive number, the sign of the answer will depend on the size of those numbers. So I can say, I don't know the sign for delta G, but I can say how the sign for delta G will change if the temperature changes, because the temperature is in this formula. At higher temperatures, this term will become larger. And if the positive term increases in size, when I add them, that'll make delta G more positive. So I can say at a higher temperature, delta G will become more positive, which means non-spontaneous. So if this reaction is at equilibrium, and when I want to shift it back toward the reactant side, I would increase the temperature. This is where this analysis is useful. I want to know how to control this process. How do I get more products, or how do I get more reactants, depending on my preference. If I want, in this particular example, if I want to get more reactants, I need a higher temperature, because at a higher temperature, the positive sign for the negative T delta S term becomes larger than the negative sign for delta H, making delta G positive, which shifts it back toward the reactant side. And so I would use a lower temperature to shift it toward the product side, because at a low temperature, this term becomes smaller and smaller, and if I take a negative plus a small positive, the negative will dominate, and I'll end up with a negative delta G, which means it's going to be spontaneous. So in this case, if I want to make as many products as possible, I got to keep the temperature relatively low. Otherwise, it'll shift back toward the reactant side. So this analysis is really important, because if I want to do this reaction, I got to be able to control it and try to increase the degree to which it shifts toward the side I desire. So here was the first quiz question related to that same topic. Slightly different reaction. So last time we determined for this reaction, because we're converting a sigma bond into a pi bond, that what's happening here is it's going from more stable to less stable, and that delta H was a positive value. So now that we've talked about entropy, we can also look at the entropy of the system. So the main thing that's happening here is the ring, which is preventing much rotational variety, is breaking open. So now these single bonds can fully rotate all the way around at 360 degrees. So with more rotational variety, there should be an increase in entropy. So that should be positive for the system. What about the surroundings? So I looked at some of your quiz questions, and I noticed that some of you were assuming that delta S for the universe is not changing. That is not true. It's true that we can't create or destroy energy, but entropy is different. Entropy is variety, and if you look at reactions occurring, and I compare the variety in the system and the surroundings, for a process that's spontaneous, overall it has to be positive. So I know that delta S total will be positive if the process is spontaneous. It could be negative if the process is non-spontaneous, but I don't usually expect it to be zero. So I can't just assume that the surroundings will have a negative change in entropy because the system is positive. They can easily have the same sign or different signs. That's what we were saying a minute ago, is to determine the sign for delta S for the surroundings, I have to look at delta H for the system. If it's positive and endothermic, it's absorbing energy from the surroundings, so the temperature of the surroundings will go down and the amount of variety in the surroundings will decrease as well, or the change in entropy or variety in the surroundings will be negative. What's the sign for delta G? Well, delta G is equal to delta H for the system minus T delta S for the system. And so mathematically I can add a negative, which is the same as subtracting. And that's the way the book likes to do it. I think it actually is helpful to see it this way, because now when we look at the sign for delta H, we have a positive number. We're going to add to that another value. And if delta S for the system is positive, a negative times a positive becomes negative. So again, I have another situation where the two terms I'm adding have opposite signs. I'm adding a positive number and a negative number. And so the sign for delta G will depend on which of those is larger. So in the last example, we saw the opposite signs for delta H and delta S. And in this example, we needed a lower temperature to make delta negative and make the process shift toward the product side. In this example, it's the opposite, because in this example, when we look at the formula here, if I increase the temperature, I'm increasing the size of the negative value. And that's going to make delta G more negative. So delta G will be more negative at higher temperature. In this case, specifically because delta S is positive. That's the difference. If you want to know how temperature will affect the sign for delta G, which affects whether the process is spontaneously producing products or non-spontaneously producing reactants, look to the sign for delta S. If delta S for the system is positive, an increase in temperature will shift it toward the product side. If delta S for the system is negative, an increase in temperature will shift it back toward the reactant side. And so a short kind of rule that you can use is to remember that an increase in temperature will always shift a process toward the side that has more entropy. Increase in the temperature here shifts it toward the reactants, because the reactants have more entropy. There's more particles there moving around with more variety than when I put them together. And when I increase the temperature here, it shifts it toward the product side, because the products have more variety. There's more variety in the ways the molecule can rotate when it's not constrained to a ring. And so all of that's explained through the math that we just did, but that's basically the outcome of that analysis. Any questions about any of that?
I have a question.
Yes.
What's an example where they would both be the same sign?
Oh, sure. So if we did something like this, um, um, let's see. Well, if I do this, just thinking out loud here, and I do an addition reaction and add the H and the Cl across there, that's going to be a decrease in entropy because I'm going from more variety to less variety when I have 2 moles and I'm going down to 1. But here I'm converting a pi bond into a sigma, so delta H would be negative. Yeah, so, okay, so that example is not a good example. That does help me to think of a good example, though. A combustion reaction is actually a great example where of what you're talking about, I think. So let's say we just had methane and we add oxygen and we produce CO2 and water. So once I balance this reaction, I'll need to get equal amounts of oxygen and hydrogen and everything on both sides. So I've got 4 hydrogen, 4 oxygen. That's not a good example. Let's go with ethane and oxygen. So now if I balance it, I'll need a 2 here to get 2 carbon on both sides. I'll need a 3 here to get 6 hydrogen on both sides. So that's, I need a 4.5 here. So we'll have to double all this to get this thing balanced. So now I've got 4 carbon on each side, 12 hydrogen on each side, and 18 oxygen on each side. So I'm starting here with 11 total moles, 9 moles of oxygen and 2 moles of ethane. And I'm producing 10 moles. That didn't work out how I'd hoped. Yeah, I'm going to have to say off the top of my head I can't think of anything. There definitely are examples where delta S is positive and delta H is negative. Is that what you're asking about?
I think so. So like when, yeah, that's what I was referring to.
Yeah, so if delta H is negative and delta S is positive, well then I'm adding negative T delta S, and a positive delta S times a negative is going to give me a negative number here. So that would be a situation where you're adding 2 negatives together. So no matter what, delta G is always going to be negative in that case. And in that case, there's no way to shift the reaction back toward the reactant side. It's always going to be product favored. There are examples of that. I can't think of any off the top of my head. I think a combustion reaction actually does fit that example, but these 2 right here don't, because the moles didn't. I didn't get more moles of products than reactants. If I have more moles of reactants, then delta S would actually be negative. But I think there are other molecules with more carbons where I end up with a lot of units of CO2 and water. And if not, there are other reactions that I can't think of right now where delta S would be positive, and so the T delta S term would be negative. Delta H term would be negative because the products are more stable than the reactants. And in that case, you have 2 negative values to add together. You're always going to get a negative delta G. There are also examples where it's endothermic, but the entropy is going down. And so a negative times a negative becomes a positive there, and I'm just adding 2 positive terms together. And so those reactions will never be product favored. They'll always be non-spontaneous or reactant favored. So that's why this analysis is so important, because I wouldn't want to run a reaction if I already knew that it was never going to give me much products, because the value for delta G is positive at whatever temperature I'm working at. All right, so hopefully that answers your question, not in a specific way, but at least in a general way. So if you recall from Gen Chem, we introduced the terms exergonic and endergonic versus exothermic and endothermic. So changing the thermic root word to gonic means we're talking about delta G instead of delta H. Right? So now we know delta H only covers the change in stability for the reactants and products. It tells us how much heat is going to be released or absorbed, and that's useful, as we talked about on Tuesday. But delta G is usually more valuable because delta G tells us if it's going to be spontaneous or non-spontaneous. And so if I factor in both the enthalpy and entropy, as we've been doing in the last few slides, and I can determine the sign for delta G, that tells me whether the products or reactants have a lower free energy. And if I can show that the products have lower free energy than the reactants, or that delta G is negative, it means it will be product favored. And the more negative the value, the more products I'll get when it reaches equilibrium. Delta G does not tell us about the rate of reaction. So that's a different analysis that we have to get to. I could also have a situation where delta G is positive. That tells me it's non-spontaneous. So again, we're not looking at the stability or the potential energies here. We're looking at the free energy, which factors in both enthalpy and entropy considerations. And so if we consider both of those and put it together with the formula to get delta G, that tells me that this process at whatever temperature we're talking about is not going to favor products, it's going to favor reactants. So this is just like a visual way of showing whether delta G is positive or negative. And what it means to favor something is that you'll have more of that when it reaches equilibrium. So if I have an exergonic process, will every molecule of A and B, will every molecule of reactants be converted into products? The answer is no. We know that from Gen Chem 2. Any process will eventually reach some kind of equilibrium. The equilibrium might be close to a 50-50 ratio of reactants and products, but if you remember from Gen Chem 2, there weren't many examples like that. Most of the time, you end up with way more products or way more reactants, and that depends not just on the sign for delta G, but on the size of it. The larger the value, the more dramatic this reaction will favor one side or the other. So if it's a very large negative, I'll have almost exclusively products. If it's a very large positive, I'll have almost exclusively reactant. And so that means that delta G is really valuable. It tells me which side of the reaction is going to be favored and by how much. And that's something we would want to look at before we run a reaction to see if it works experimentally. So obviously I don't have just a couple individual units of these things. I've got moles of them. And so we want to make sure we understand that as a reaction progresses, it's not like one reaction is going to eliminate all of the A and B from solution. The amount of A is going to slowly decrease, and the amount of products are going to slowly increase. Once it gets close to equilibrium, it's going to slow down. The amount that this goes up and down is going to be changing at a slower rate. We'll talk about rate in a minute. Eventually, though, I never convert all my reactants into products. As we said, we get an equilibrium. So we also want to understand why we're getting an equilibrium from a couple different conceptual perspectives. So first of all, you got to also remember that collisions are necessary. So in order to convert whatever reactant, so maybe we can go back to this one here, where I've got these pi bonds are going to shift around and they're going to produce this product here. In order for electrons to move, they have to leave the orbital they're in and move into a new orbital. Leaving an orbital doesn't just happen. because a pair of electrons in an orbital is attracting to those nuclei. In order to get it to move to a different spot, it has to break those attractions, and that requires a collision. So collision is your source of energy. Source of energy needed to disturb the electrons in their current arrangement and give them the energy they need to move to a different spot. So if all my reactants start in one form, and that's the only type of molecule I have around, there's going to be a lot of those, and they're going to be colliding a lot. And initially I'm going to start to form a lot of products. Once some of the reactants, so if I have like a sample and I've got a bunch of reactants, once some of the reactants get converted into products, now there are fewer reactants around. So if I have 10 of these, there's maybe a chance that one will react every 2 minutes. But if I have only 3 or 4 of them, there's a chance that one will react maybe now every 5 minutes or 15 minutes. So the rate at which reactants is converted to products starts to decrease. And if there's only few, and they're not colliding very often, I'm not going to get many products to continue to form. But then as the products form, now they start colliding, maybe with a solvent or the container or with one another. When the products start colliding and the amount of product starts to build up, that's when it starts to go back. So from that perspective, you eventually reach a dynamic equilibrium where if the reactants react a lot and form a lot of products, well then the products will start colliding with things and converting back to reactants, and reactants will convert to products, and products will convert to reactants, and eventually I'll get a ratio of the two that's not changing anymore. So that's an equilibrium because the net amounts of reactants and products aren't changing, but it's still dynamic because the process is still occurring. Reactants are now and then colliding and converting to products, and products are now and then colliding and converting to reactants, and I'll end up with some ratio of the two that's not changing, but the reactions are still continuing, which is what they mean when they say it's dynamic. So once the rate of the forward reaction and the rate of the reverse reaction are the same, there's no net change in the amounts, and that's when you've got an equilibrium. So in terms of the value for delta G, and this relates to one of the other quiz questions, eventually if I look at this reaction where my reactants have maybe a higher value in free energy than my products, so the products have less free energy than the reactants, and that's going to be some combination of them being either more stable or having more entropy, right? So S, entropy, and enthalpy are my key factors. So if the products have lower free energy than the reactants, it's because they're either more stable or they have more variety or some combination of the two. Maybe they're not more stable, maybe they're less stable, but they have so much more variety that overall they have less free energy. There will be a point though that has even less free energy, and that's the minimum amount of free energy that the system can reach. So it'll eventually go down, and that's where my equilibrium is, at the point where the free energy is the lowest. So why is there less free energy here than on the products or the reactants? Well, that has to do with entropy, right? So we said that why does the equilibrium have the lowest free energy, lower than the reactants or the products? Because it's a mixture. Here, all my molecules look exactly the same. Here, all my molecules look exactly the same. I've got pure products or pure reactants. But if I have an equilibrium, I've got some of the reactants present and some of the products. I have more particles and a greater variety of particles. So the mixture at equilibrium will always have more variety than either pure reactants or pure products. And that's what this is getting at. How would you compare the variety or entropy if I have a mixture of all four versus all my molecules looking like products only? Well, there's going to be more variety if I have a mixture of everything all mixed together. And so if we think about that in the context of this specific example here, this process, maybe it favors the reactants. But if all my molecules look like reactants, there's never going to be as much entropy or variety as there would be if I had at least some products around. So an equilibrium is always reached where you have at least something on both sides. If the reactants are way more stable or they have way more entropy, there might be a lot more reactants than products at equilibrium, but I'll have to have something of both in order to get to the maximum degree of variety, which correlates with the minimum value for G, and that's the equilibrium point where there's no net change anymore. And that's really the answer to this quiz question. So why is an equilibrium mixture lower in free energy than the pure products or pure reactants? Well, when I have a mixture, there's just going to be more variety. So even if the product have a lot more variety than the reactants, and you're thinking, well, if there's any reactants at all and they have less variety than the products, then having some of those reactants present is going to decrease the variety, or it's going to decrease the entropy. And that's not favored. So that might be a situation where I end up with almost exclusively products, but there's at least going to be some reactants to increase that variety. If everything were to shift 100% to one side, it's just not going to create as much entropy or variety than there would be if there was at least some degree of a mixture. So when we talked about reaching equilibrium in general chemistry, we said because the reaction is shifting now at equilibrium in the forward direction at the same rate it's shifting in the reverse direction, the quantity of products and reactants are no longer changing. So the ratio of products to reactants remains constant. That's only true at a certain temperature. If I change the temperature, the ratio might change. And so let's say I have a constant temperature, then the reactants or the products over reactants, it should give me a constant ratio, assuming that I take into account the stoichiometric coefficients, right? So if I had two molecules of A reacting with one B to produce maybe three C's and one D, in order for this to be a constant, hopefully you recall, the coefficients become exponents for the substances that they're modifying in the balanced equation. So it's only a constant, products of reactants is only a constant if I put the coefficients in as exponents. And this equation from Gen Chem 2 hopefully also looks a little bit familiar to you. So if you calculate delta G from this equation, delta H plus negative T delta S, which we just saw. If I know the enthalpy change and the entropy change, and I actually have numbers and I know what temperature I'm running it at, I can plug that all in to get delta G. Then, if I want, I can solve this and determine the equilibrium constant. Alternatively, if I can measure the equilibrium constant by figuring out how many moles per liter, these brackets mean moles per liter or molarity, how many moles per liter of products and reactants there are, and plug that all in, I can get the equilibrium constant. And then I can do the math here and figure out the sign and value for delta G. So you should be able to work with these equations just like we did in Gen Chem 2. And all of these terms are thermodynamic terms. So thermodynamics is all about products versus reactants. It's all about equilibrium. When the reaction reaches equilibrium, I gotta have more products or more reactants. None of these terms relate in any way to how quickly the process will reach equilibrium. And that is kinetics. That's about rates or how fast the process occurs. And that's a totally different analysis. So throughout the rest of the semester and into Organic Chemistry 2, we're going to be focusing a lot on the difference between thermodynamics and kinetics, because when you get them confused, it causes a incorrect analysis for the reaction. So thermodynamics allows me to determine if I were to allow enough time for it to reach equilibrium, which one I would have more of. And that's what delta G and KQ are all about. It doesn't tell me how long it's going to take to get to equilibrium, though. Kinetics helps me determine how fast it will take and what the rate will be, or like how many molecules are reacting per minute or per second. Kinetics also relates to the mechanism. And so we're going to see, starting in the next chapter, how if I can look at the kinetics of the process, or how often the molecules are colliding, that helps me get a lot of information about the mechanism, which is a picture of what the steps are in the reaction. So if I have A and B converting into products, does that just involve one simple collision and then all the electrons move at once and A and B are converted to C and D in one step? Or do they first have to collide in some way and then maybe bond together, and then maybe a different collision has to occur where A is converted into some intermediate, and then the intermediate undergoes another collision and produces a product. So sometimes reactions have to go through multiple steps before they can actually produce the products, and kinetics gives us a clue about the steps that are involved, and we're going to see how that works. So we want to make sure we understand the difference between thermodynamics and kinetics. Kinetics is about the process and how long it takes. Thermodynamics is about comparing the initial versus final states. It doesn't tell me anything about the process that the reaction has to go through in order to get from reactants to products. So this chart here just gives you a sense for the magnitude of the value for delta G and how that relates to equilibrium. So if we calculate delta G by plugging things in, you can also plug in delta H and delta S, plugging that in, getting the value for delta G in units of kilojoules per mole. The value doesn't have to be that large for it to be a situation where the equilibrium greatly favors one side or the other. So we do know that if the delta G is negative, when it reaches equilibrium, I'll have mostly products, right? Because equilibrium constant's products over reactants. So if I get a value greater than 1, it's product favored. And I'm going to get a lot more products than reactants, even if delta G is just slightly negative. It creates an equilibrium constant significant enough where I have mostly products and very few reactants. And the opposite, obviously, if delta G is positive, I get an equilibrium constant less than 1, and I get very few products forming. Right? So that's the value in determining, if I can determine not just the sign, but also the number, it allows me to calculate, am I going to get a lot of products, or is it going to be very little products? And that's going to depend on the sign for delta G and the equilibrium constant. So now we're going to talk about kinetics a little bit. So that's our review of thermodynamics from Gen Chem 2. It's not a very thorough review. Obviously, we're limited on time. But those are the main points that are going to be relevant moving forward, the main things we're going to refer to when we talk about thermodynamics. So we're going to switch gears a little bit, start to talk about kinetics. As we said, kinetics are all about how fast something occurs or the rate at which it's occurring. That has nothing to do with whether it's spontaneous. That's a common confusion. In English, when we use the word spontaneous, usually we mean that something's happening quickly. I spontaneously decided to go out and get a coffee or whatever. That means it was all of a sudden. That's not what we mean here. Spontaneous in chemistry means that it's product favored, or it's going to get to equilibrium and have more products than reactants. That might happen quickly. It might happen very, very slowly. So if it's fast, it might be an explosion. Other examples of very fast reactions are acid-base reactions. Acid-base reaction is a simple reaction. It involves the base picking up the proton, the electron staying behind, and since these bonds are usually don't require much energy to break, the reaction occurs relatively quickly. It reaches equilibrium very fast, similar to an explosion, not quite that fast. There are many non-spontaneous processes that also reach equilibrium quickly. So don't, in your mind, correlate the fact that a reaction is product favored with the fact that it happens quickly. Because there are also lots of examples of product favored reactions that happen very slowly. If you have any diamond jewelry, at the moment, it's in the process of being converted into graphite. The value for delta G in going from diamond to graphite is negative. It's happening spontaneously. Luckily for you, the rate of that reaction is very slow. So the rate at which carbon diamond is converted into carbon graphite happens on the order of millions of years, so you don't have to worry about your diamond disappearing and turning into graphite at any time soon. But it is happening because the graphite has a lower free energy than the diamond. And other examples include like rusting. It's a little bit faster than diamond converting into graphite, but still a very slow process. Iron ions are favored over neutral iron because the outer electrons are not held very tightly to the nucleus, and other atoms attract them better. They start falling out and creating an ion. That happens spontaneously, but it also happens quite slowly. So just make sure you don't think that there's a relationship between how fast something happens and how product favored it is, because there is no direct relationship between those two. So kinetics is all about really how many molecules or how many moles of molecules are reacting in a given period of time. So the units for rates are usually going to be moles reacting per second. But since it's hard to measure moles, and also the concentration affects the rate, right? We were saying that if I have a sample with only a couple reactants around, I'm only going to have maybe one or two reactions per second, but if I've got it packed full of reactants, they're going to be colliding all over. I'm going to have a lot more reactions happening per second. So the number of reactants in a certain volume can affect the rate. And so since the number of moles per volume or per liter has an effect on the rate, usually rate units are listed in moles per liter reacting per second, or molarity reacting per second, right? Molarity is the same as moles per liter. And the number of moles that will react in a given liter per second depends on a variety of factors. It depends on how often those reactants are going to be able to collide with sufficient force to move the electrons around. So if I have a sample or a reaction where A and B have to collide to produce product C, if I have very few A and B and they're just bouncing around randomly, how often are they going to collide? Not very often. So the rate is not going to be very fast. So we're going to talk about the factors that affect how often reactants are going to collide with the energy necessary to rearrange the electrons from their current positions to create the products where the electrons are arranged differently. So here are the factors that affect that. We just said the concentration is a big factor. So if I increase the reactant molarity, remember these brackets mean molarity. If I increase the molarity, what effect will that have on the rate? It will increase the rate. And that's because, as we just said, if I have lots of reactants around versus very few, and they're just bouncing around randomly, if there's a lot of them packed in a small amount of space, which is what molarity measures, the number of moles per volume per liter, if there's a bunch of them, then they're going to be constantly colliding. And I'm going to have a lot of collisions per second. So if I can increase the number of effective collisions per second, that will increase the rate. What makes a collision effective? Well, it has to be, sometimes it has to occur in the right orientation. Sometimes if molecules collide head-on, nothing happens. One has to collide on the backside of the other, for example. The collision has to occur with enough energy. If it's just a very mild collision because they're moving slowly, they'll probably just bounce off, nothing will happen. So we're looking for effective collisions, collisions that have the energy and orientation necessary that when the molecules collide with enough force and in the right orientation, the electrons can be rearranged to produce the products. So the more reactants I put in a given amount of space, the more often they'll be colliding, and the more often those collisions will be effective, and the more product I'll make per second. So I can increase the rate by increasing the molarity. And that's expressed mathematically. So we're going to talk about these other factors here in a minute. We just want to explain how this factor is expressed mathematically. And so if you recall from Gen Chem 2, we talked about the rate law. The rate law is a mathematical expression that says the rate's equal to the rate constant times the molarity, the concentration in molarity. So if I increase the molarity, I increase the rate, right? We see the mathematical proportionality of that right here. Assuming the exponent here is 1, if I double the molarity by putting twice as many reactants in a given amount of space, they should have twice as many collisions. And the rate should go up by twice that amount. Sometimes the exponent is not 1 though. Sometimes it's 0 or 2. If you remember that from Gen Chem, there are a variety of different processes that might result in different exponents here in the rate law. So those are called the order of reaction. Right? So if I have two reactants, the exponent, each reactant will have its own exponent, and that exponent governs the relationship between the molarity of the substance and the rate. So let's look at that in a little bit of detail. So let's say I have a reaction. It's known to be first order with respect to A, so that means the exponent for A would be a 1. And I know that it's 0 order with respect to B, so the exponent for B is a 0. So we want to write the rate law. It would be rate equals the rate constant times concentration of A. And if something is taken to the 0th power, any value to the 0th power equals 1. So I don't need to even put that here because I'm just multiplying by B to the 0th power, multiplying by 1. Multiplying anything by 1 doesn't change it, so I don't need that. So ultimately, the rate law expression could exclude one of my reactants if that reactant is 0 order. So if I then double the concentration of A, so let's say I do this reaction, I measure how many units of A are reacting per second, and then I double the number of units in a given amount of space. So not just doubling the number, I'm packing twice as many into the same amount of space. So if I have a certain number in that space and I pack in twice as many into that space, if it's first order and the exponent is a 1, which I might not show because leaving the exponent out implies that it's a 1, if I double that by putting twice as many in, the rate will end up doubling. And mathematically that should work because 2 to the first power is 2. And so if I multiply A by 2, I'm really multiplying it by 2 to the first power or 2. And if this is equal, I have to multiply the other side by the same amount for it to remain equal. So doubling the concentration of a reactant that's first order would cause the rate to be doubled. What if I double the concentration of a reactant that's 0 order? Well, that would not affect the rate, right? Because first of all, we simplified this rate expression so that B wasn't even included. So any change in the concentration of B, there's no way to account for that in the equation. But if I did include it and include the fact that it's 0 order, no matter what value I put in here, I could double it, I could triple it, whatever I do, no matter what the value is, taking it to the 0th power just means it's equal to 1. So in that case, if I double the concentration of A, the rate doubles. If I double the concentration of B, no change in the rate. So this is how the exponents are determined. If you remember from Gen Chem 1, you run the reaction, you measure the rate, the instantaneous rate at time 0. Just to review that, if I have my reactant and I plot that over time, in the beginning I've got lots of the reactants around, so the concentration is relatively high in the beginning. Over time, as the reactants get converted into products, the amount of reactants go down. Initially down deeply, kind of level out. So the initial rate is the slope at time 0. That's my initial rate. So I measure that with a certain amount of A in one experiment, and then I double the amount of A and the molarity of A and measure the initial rate again. If I show that the rate doubles, that tells me that A was first order. If I show that doubling the molarity didn't have any change in the slope of this line initially, or any change in the rate, that tells me that that reactant is 0 order. So if there's a change in the reactant molarity, but it does not affect the rate, it's a 0 order reactant. Right, so here's a scenario where they're both first order. Right, so this is really not very different from what we just said. The rate law would then be the rate constant times A to the first power times B to the first power. So everything's multiplied together over here. If I were to double A, since it's first order, that would cause the rate to double. Now that B is first order, if I double it, it's not to the 0th power, so that's actually going to make a change. If I double this, the rate would double, or the slope of that line would become twice as steep in the beginning of the reaction, because now I've added more particles and they're going to collide more often, and those collisions are going to create more products in a given amount of time, so the rate at which product is produced would also double. So anytime something is first order, it's first order because doubling the amount of the substance in a given amount of space causes a reaction to happen twice as fast, because there are twice as many collisions and twice as many effective collisions. So here we still have the same thing with B, so we already talked about that. But what if one of my reactants was second order? So if A were second order, the rate law would be rate equals rate constant times A to the second power times B to the first power, assuming B is still first order. So if I were to double B, because it's 2 to the first power, 2 to the first power is 2, and that would cause the rate to double. We just said that on the last slide. If I double the concentration of A, because A is second order or squared, if I doubled A, I'm really taking it times 2 to the second power. And so because 2 to the second power is 4, that would cause the rate to quadruple. So the rate would quadruple in that case. And more generally, we can say if a reactant is second order, meaning its exponent is a 2, then any factor that reactant molarity is multiplied by the rate will be multiplied by that factor squared. So if I triple the molarity, 3 squared is 3 times 3 times 3, or no, 3 squared is 3 times 3, I would experience a 9-fold increase in the rate. If I quadruple the molarity, 4 times 4 is 16, I'd see a 16-fold increase in the rate. So when I have a second order reactant, it means the rate is exponentially dependent upon that molarity, or that particle is very involved, extra involved in the collisions, because having more of them creates more collisions. Normally having twice as many just creates twice as many collisions, and the rate goes up twice. But this tells me that two of these must somehow be involved in the mechanism. I've got highly dependent reaction on the amount of A, because the rate at which the collisions occur is exponentially dependent upon the amount of the reactant present. So we'll talk more about that as we see more specific examples. So that pretty thoroughly, at least for now, talks about how the concentrations of my reactants affect the rate. We want to look at activation energy next. So activation energy is the amount of energy required to break up the reactants before they can be produced into products. So there's got to be some original arrangement of electrons and some stability associated with that, and I've got to break some of those electrons away from the nuclei they're originally attracted to if I want to rearrange them into the form of the products. So this top point of this curve is where the electrons are broken away, or at least partially broken away. They're not knocked out completely or anything, but they're not in the orbitals anymore. Partially broken away from their original orbitals. And that is really unstable. That's a maximum, a local maximum, or a maximum energy point. It's really unstable and disfavored, because the electrons need to be in orbitals. They need to be in an atomic orbital as a lone pair, or in a molecular orbital as a bonded pair, surrounding nuclei forming attractions. If I break them out of their orbitals for just a tiny moment, it's really unstable during that moment. And so it requires energy to get there. The reactants will always be lower energy than the transition state, this is called. Because the reactants have the electrons in orbitals surrounding nuclei. And when a bond starts to stretch or break, the electrons are no longer in the proper orbitals, and they become really unstable for a second. So in order to get from reactants to products, first, the electrons have to be broken away from their orbitals and have to first get to the transition state. And the amount of energy necessary to do that is called the activation energy. Why must energy increase before the product can be formed? Because you have to break up some of the initial attractions. You need energy to break attractions and move the electrons out of their orbitals so that they can then be made unstable enough to rearrange into new orbitals to make the products. The amount of energy required to convert the reactants into the transition state is going to be different for different reactions. And that's because some reactions require multiple bonds to break. When the bonds are breaking, depending on the elements involved, they may be more or less stable. So we can say the electrons' stability changes when they're knocked out of their orbitals, depending on the elements involved, as well as the number of bonds breaking and forming. If I have to break 2 or 3 bonds all at once, it's going to take a lot more energy to break all those bonds and move the electrons out of their orbitals. If I have electrons that are held in really nice and tight initially, and they're forming really strong attractions to their nuclei, it's going to take a lot of energy to knock them out of there, and so the activation energy will be higher. So when it comes to rate, we're interested in how many of these reactants undergo the process where they're producing products per second. And that depends on the quantity of energy I have to put in, and it depends on the temperature a lot as well. So the temperature supplies the energy necessary. But the electrons are not just going to jump out of their orbitals. They would never do that. To move an electron out of an orbital so it can rearrange into a different position, a collision is required, and the temperature or the molecular motion is what provides the collisions, right? So if I have a sample and my particles are at a very low temperature, they're sluggishly moving through space, and if they collide, the collision won't really have much energy, nothing will happen, because the collision doesn't have enough energy to break the attractions the electrons have initially, so I can't rearrange the positioning of the electrons. So if I increase the temperature, I'm increasing the amount of average kinetic energy for the particles. So some of the particles still move slowly, but the number that are moving fast increases. And now there's a chance that they'll be flying through space fast enough that they'll collide with enough force to overcome this activation energy barrier, knock the electrons out, and then the electrons can rearrange to produce the products. So would you expect there to be a temperature below which the reaction rate is 0? Well, probably the reaction rate would be 0 if you had, if you're at absolute 0 Kelvin, because there wouldn't be any motion, you wouldn't have any collisions. But within reason, most of the time, the reaction rate at least is still a non-zero value even at very low temperatures. And the reason for that is because temperature represents the average kinetic energy. So if I've got a sample of reactants and they're bumping around and moving around in here, even at a very low temperature, where on average my molecules are moving slowly, there's probably a couple that are moving relatively fast, right? Any sample at some temperature, the temperature doesn't tell me that all the particles are moving at the same speed. Some are moving faster and some are moving slower. So there'll always be some fraction of the molecules that are moving fast enough that they'll collide with enough energy to produce a transition state and start to make the products. There's also no temperature above which the reaction rate would be instantaneous. So what I mean by instantaneous here is all of the reactants convert to products at once. You're not going to see that very much, because even if I increase the temperature a lot, since temperature represents the average motion, there's usually a few that are still moving pretty slowly. And so unless something collides with them really fast, that collision is not going to supply the activation energy necessary to get to the transition state. So keep in mind that the temperature measures the average amount of motion. So if I increase the temperature, I will increase the speed on average, and I'll increase the percentage of the collisions that occur with enough energy to produce products. So I'll start making products at a faster rate. So increasing the temperature increases the rate. And if I'm looking at the rate law, how does that happen? It doesn't affect the values for, say these are both first order, just for example. Increase in the temperature doesn't change the molarity. Increase in the temperature changes the rate constant. So if you remember from Gen Chem, the rate constant is only constant at a given temperature. If I change the temperature by increasing it, the value for the rate constant will increase. That's how the rate goes up. So we know conceptually increasing the temperature increases the percentage of the collisions occurring with enough energy to break the electrons away from their original arrangement and allow them to form a new arrangement. And it does that by increasing the value for the rate constant. In terms of the activation energy, what we were saying a moment ago is that some reactions maybe only require some weak bonds to break. If the bonds are already weak, it won't take much of a collision to break them. Other reactions have much higher activation energies. Notice that the activation energy is not dependent upon the enthalpy change, right? So to go from the starting energy to the final energy, this is a negative delta H. This reaction over here gives me almost the exact same negative delta H. So the size or magnitude and sign of the delta H value is totally separate from the value for the activation energy. I can have a small activation energy and a very negative delta H. I can have a small activation energy and less negative or even a positive delta H. So I could have a small activation energy and then the products are maybe still higher in energy than the reactants. I could have a very high activation energy and still have a very exothermic process or an endothermic process. So the energy relationship between the reactants and products is separate from the energy relationship between the reactants and the transition state. The activation energy does give me information about the rate. If the activation energy is a large value, like over here, it means only the strongest collisions will have enough energy to break the electrons away from their initial arrangement, and so the products will only form very rarely. If only the strongest collisions can make it up here, then most of the collisions don't produce any products. So we're talking about how many effective collisions occur per second, or how many collisions can produce the energy necessary or involve the energy necessary to break the initial arrangement of the electrons and attractions of the electrons to then allow them to rearrange and produce the products. And this chart shows how temperature affects the number of effective collisions. So as we were saying, temperature measures the average kinetic energy of the particles or molecules present. So if I'm at a lower temperature, the energy, the kinetic energy that they have is on average not a lot. It's a small amount of energy. Some of those particles, so the higher up here means I have more molecules at that energy. So the peak means this is the average, or most of the molecules have this amount of energy. So if I'm down here on the line, there aren't very many molecules. The number of molecules having this energy is very small, but there's some molecules that have, even though the population is low, there's some molecules that have almost no energy. Those ones, when they collide, aren't going to do anything. So if this is the energy my collision needs to have, this is the activation energy, only particles that collide with that amount of energy or more are going to be able to start producing products. So at the lower temperature, the blue line shows me the number of particles that have the energy necessary is a very small number at low temperatures. If I increase the temperature, what happens to the line? The average shifts to the right and the distribution gets broader. The distribution still includes molecules with very, very little energy, but the blue line kind of stops here. There aren't really any molecules with more energy than this. The red line goes all the way out here. So the red line includes a number of molecules with more energy, and so it still includes molecules with very little energy, and so the distribution is much broader. And the net effect of that is that I have a greater population of molecules that have the energy necessary when they collide to start producing the products. So that's why if I increase the temperature, the rate of reaction will increase because I have more molecules that will be colliding with enough energy to start making the products. So the next factor is a catalyst. So we'll talk about geometry and sterics a little later. I'm not sure if that's something, I think we'll probably talk about that next time. Oh no, it's right here, sorry. I guess I didn't prepare too much to say about that, but geometry and sterics affect the reaction rate. So there are some examples of this, so I'll just give you one example. So let's say I've got a carbon and I've got a bromine attached to it. This is one of the first reactions we're going to see in detail a little later. And so then let's say I've got some hydrogen here, and I want to bring in a chlorine to replace that bromine. I want to make a molecule that has chlorine there. So I want chlorine to come in and form a bond to the carbon, but I can't make a 5-bonded carbon, so the bromine would have to leave. And that would produce a new bond between the chlorine and the carbon. And then the bromine would take those electrons and have them as a lone pair. In terms of geometry, what we mean here is that this reaction will only occur if I get an effective collision. The collision between the chlorine and the bromine, or the chlorine and the carbon, has to be hard. It's got to be forceful enough to break this initial pair of electrons that's shared and stabilized away from the carbon. So I need a high energy collision, and in terms of the geometry, it has to collide in the right spot. If the chlorine were to come around and collide on the other side of the carbon, there'd be no reaction. So by geometry, what we mean is the correct orientation in the collision. The two atoms that are colliding can't just collide in any old orientation. They have to face one another in just the right way, and the collision has to occur between them in the right spot. So if there's a requirement like that for the reaction, and the collision will only be effective in producing products if it occurs in the right spot, there's going to be a limit to how often that can occur, because these collisions are random. Randomly, how often is the chlorine going to bump into just the right spot on the carbon? Not very often, so I'm not going to produce the products very often. So the rate will decrease when the geometry, when the geometric conditions are very specific. If any old collision will do, it'll happen more often. But if the geometry involved or orientation of the collision requires a specific type of collision, it's not going to occur very often, or the rate will be slower. In terms of sterics, if I made these CH3 groups, now not only does the chlorine have to bump into the carbon in the right direction, but now I've got these much bigger electron clouds blocking it out. So the rate at which that can happen will be almost never. So even though this reaction might be product favored, because the products have either more stability or more entropy than the reactants, the rate at which it can happen is pretty much never, because the sterics, or crowding, or electron clouds right in the area where the collision needs to occur, are blocking the collision. So there are a lot of factors that can affect how often the effective collisions between molecules will occur. So that's geometry and sterics. The next factor is a catalyst. A catalyst has the opposite effect. If a very specific geometry is required, or there's too much sterics around the area of collision, the collision will almost never happen. A catalyst increases the effective collisions. So it increases the rate by increasing how often, the frequency of effective collisions. Oops. And that is because a catalyst is involved in the collisions, and it lowers the activation energy. So a catalyst will typically stabilize the molecule in the moment during the collision. So with the catalyst, it stabilizes, usually, the molecule during the collision. It might do that by coming in and forming some intermolecular attractions right at that moment where the electrons are breaking away. If they can form an attraction to the catalyst, it won't be so unstable. Without the catalyst, it will be much more unstable, because I have to break all these electrons away from their orbitals at the same time. So a catalyst makes the pathway lower in energy by making it more stable during the collisions, and so it can happen a lot more often. Without the catalyst, only the strongest collisions would have the energy necessary. With the catalyst, most of the collisions have the energy, so there'll be a much more frequent effective collisions per second. So to re-emphasize the difference between kinetics and thermodynamics, kinetics mainly focuses on the difference in energy between the reactants and the products, or how often are these collisions going to have the energy necessary, the orientation, the ability to overcome sterics, to collide with enough energy to move the electrons out of their current arrangement so that they can be arranged. The energy of the product doesn't matter. How often the products will be produced here, it doesn't matter if the product is stable or even more stable, or if it's not very stable and its energy is up here. It doesn't matter. What matters is the energy of the reactants and the transition state, because once we get up there, the products will happen immediately. So that's the barrier we have to get past, and that's our concern when we're worried about kinetics or how often the reaction will occur. In contrast, if we're in thermodynamics, we don't care about this. It could happen very quickly, or I should say very often. It could happen almost never if the activation energy barrier is higher. That doesn't matter. When we're dealing with thermodynamics, we're interested in what is it going to be like after all that, once it gets to equilibrium. And the answer to that question depends on the difference in free energy between the reactants and the products only. If the reactants are higher in free energy than the products, I'll get more products at equilibrium. If the opposite, I'll get more reactants at equilibrium. It doesn't matter how often it happens. That's a kinetics question. If we're dealing with thermodynamics and we're looking at delta G or the equilibrium constant, that only depends on the relative free energies of the reactants and the products, not the energy during the transition state. So here we have a picture of two different pathways, two different reactions. So A and B, if they collide one way during the collision, it doesn't require too much energy, and they produce products C and D. If they collide in maybe a different orientation, maybe different bonds break, it's less stable during those bonds breaking, and it produces E and F. So which pathway is favored? Well, the pathway that's favored kinetically in this case is the same as the pathway that's favored thermodynamically. So some reactions just happen more often because they have a lower activation energy. If the activation energy is lower, it'll happen more often. So in this case, the blue pathway happens more often. If it happens more often, and the products are also favored more because they're lower in free energy, I'm really not going to get any of this. If once in a while A and B collided with a different orientation and made it up to this energy, and that happened once in a while and produced E and F, well, there'd probably be enough energy then for E and F to collide back and go back to A and B. And then since A and B most of the time are going to collide through the other pathway because the collisions don't require as much energy, once it gets down to C and D, that's not going to go back as often because it's so much lower energy. To go back, it would require all this energy to be put in a collision, and it won't happen very often. So if I let this one get to equilibrium, I'm going to have almost exclusively C and D because it's lower in energy in the end. And I also make it more often, so even the beginning of the process, since the collisions occur more often that way, I'm going to favor C and D no matter what I do. So will a decrease in temperature affect which pathway is favored? No. I'm going to get this pathway more often, and when it reaches equilibrium, I'll have more of it because it's lower in free energy. Will an increase in temperature affect which pathway is favored? No. Even if I increase the energy, so there's enough energy for the particles to collide and go through this higher pathway and produce the products, since those products are higher in energy than these, eventually when it reaches equilibrium, most everything will be in the form of the favored products. So this is a situation where I really can't get A and B to convert into E and F. I can mostly only get them to convert into C and D. Here's an alternative situation, and as we look at specific reactions starting next week and the following week, we're going to see some instances where this is the case, where there's two pathways and one is kinetically favored because it occurs with a lower activation energy and happens more often, but the other is thermodynamically favored because even though it has a high activation energy and doesn't occur very often, if all of this were to reach equilibrium, eventually the equilibrium would give me the products that are favored thermodynamically. So which way is kinetically Which pathway is kinetically favored? The pathway that gives E and F. They're always going to form more often because there's just going to be more collisions that occur that have this amount of energy than occur with that amount of energy. But which pathway is favored thermodynamically? The pathway that produces C and D. So this is useful because this is a situation where temperature can be used to control which set of products I get. And it really should be temperature and time together. Because if I wait indefinitely, if I don't factor time and I just wait forever, no matter what, eventually this is going to reach equilibrium and I'm going to have more of C and D no matter what temperature I use if it reaches equilibrium, because C and D are favored and lower in free energy. So what I would do here is, if I want to produce E and F, I need a relatively low temperature and a short period of time. Because if I keep the temperature low, almost all my molecules will not have the motion and kinetic energy to collide with enough energy to get through the higher energy transition state. So I'll produce very little C and D, especially in the beginning. Most of the collisions will end up being able to go through the lower energy pathway, and I'll start to accumulate E and F initially. I don't want to wait too long though, because over time, when E and F form, they'll start colliding and they'll start reacting back to A and B. And then once in a while, if the fastest moving units of A and B collide, they might have enough energy to produce C and D. And at that point, it's not going to go back much, because to go back from C and D, those collisions require this much energy, and that's almost never going to happen. So over time, or at a higher temperature, I can produce C and D. If I increase the temperature, then even if E and F form more often, which they will because there's a lower energy transition state, they'll start reacting back, and eventually once in a while I'll get the reaction to produce C and D, and then that's kind of like not very reversible because the energy required to go back would be so great. So if I increase the temperature or increase the time period, basically those two factors are just allowing me to get to equilibrium sooner. And since the equilibrium favors, in the end, whatever has the lowest free energy, that's how I produce mostly C and D. So if I have competing pathways, one's favored kinetically, the other's favored thermodynamically, I can use the temperature control. And that was exactly what this other quiz question was about. So the answer to this quiz question is basically the conversation that we just had. So if you have questions about that, you can message me. So a couple more quick terminology. I realize this lecture is going over time a little bit. Obviously, if you have to go, that's fine. Feel free to jump off. And you can always watch the video later. But as we were saying before, sometimes a reaction doesn't happen in one step. So sometimes A and B have to collide in a certain way that requires a certain amount of energy. And after they do, they might be converted into C. Maybe they combine together to produce a new substance. But that's not the end product, because that still has a fair amount of energy. It's relatively high in free energy. I'm not going to produce much of that. When it forms, it might collide and go back to the reactant side. So these steps are pretty much always reversible unless they involve a very large activation energy, and then they won't happen very often, and the reversibility of it will be minimized. But once I produce an intermediate, maybe it collides with something to produce a different transition state. Maybe I'm breaking and forming a different set of bonds, so a little bit different amount of energy is required, and then maybe that produces another intermediate, and then that has to collide with something to produce the next transition state, and then maybe the products are produced after that. Some reaction pathways have dozens of steps. Most of the reactions we're going to look at this semester have 2 or 3 steps, maybe up to 5 or 6 mechanism steps. So this is a 3-step mechanism. The reactants have to collide to produce an intermediate, which collides to produce another intermediate, which collides to produce the products. each step in the mechanism has a different transition state at a different energy. And so we're going to be applying this idea to a lot of specific reactions where hopefully it'll be more clear to you maybe once we put it into the context of some specifics. So here's that reaction we were talking about a little while ago where the carbon-bromine bond is going to break. It's called a substitution reaction. We're going to talk about this reaction in a lot of detail starting in chapter 7. And so what has to happen here is the chlorine has to collide in a very specific orientation, and since these hydrogens are small, they're not too big of electron clouds to block the chlorine from coming in. So the chlorine once in a while will collide there, and when it does, to start forming a bond, I can't make 5 bonds, so at the same time the bromine has to leave. Is the bromine going to leave first? No, if it left first, it would produce an unstable carbocation. Why would the carbon just lose those electrons? I mean, it could happen, but it would require a really strong collision. So what happens here is the chlorine comes in and starts to form a new bond as the bromine's old bond is breaking. And so the transition state is the moment, as we said, when the electrons are not properly in their orbitals. Right? When this sigma bond exists as a sigma bond, the electrons are surrounding both atoms. When the bond starts to break, we use an extended dotted line. That indicates the bond breaking, that the electrons are starting to be pulled away from the carbon. They're not really in an orbital right now. This is really unstable. They're not in the sigma bond because the bond is stretching and breaking, but they're also not quite yet existing as a lone pair in the bromine. So they're not in a proper orbital, and that makes them really unstable. And the chlorine has started to come in and form the new bond, but it hasn't yet formed the new sigma bond between itself and the carbon. And so without forming the sigma bond that the electrons can attract to both nuclei, it's really unstable. So the transition state can often be represented by showing the bonds breaking and the bonds forming as extended dotted lines. And that should hopefully prompt you to remember that this is really unstable. It's the highest energy point when the bonds are in the process of breaking or forming because the electrons are not properly in an orbital. And that's an energy maximum, a local maximum, or the highest energy point. So as soon as that occurs, instantly one of these bonds will break and the other bond will form. So it could go back, or this bond will break and this bond will form, and it can go forward. It exists for a tiny moment in time. It's too fast to even be observed by any instrumentation. So the existence of the transition state is a theory because we can't directly observe it. It's generally accepted as correct because it explains a lot of experimental data, but we can't see it, and so we're basically just assuming that as these bonds break and form, it makes the electrons quite unstable because the electrons are not in an orbital very close to nuclei. They're kind of out there in no man's land. Here's another quick look at a reaction. Here's a two-step mechanism. So in this particular case, this bond is going to break first. So as in the first transition state here, we'll call this transition state 1. What's going to happen there is this bond between the carbon and the bromine starts to break. The bromine starts to rip the electrons away from the carbon. That requires a collision. So this molecule, if it collides lightly, it won't happen. But if it collides really hard, and the collision has the energy to overcome the electron's attraction to these two nuclei, and it causes the bond to start stretching, if the electrons go with the bromine, it starts to pull them away, it starts to become negative, and the carbon starts to become positive. Once the bromine's able to pull those electrons away completely and put them into an actual orbital instead of having them in an area where they're not close to either nuclei, now they're at least close to the bromine nuclei. That's more stable than during the moment of the collision. So the transition state where the collision is actually occurring is always the least stable point. Even here where the carbon has an incomplete noble gas configuration, it's relatively unstable, but at least the electrons are in orbitals close to nuclei versus in the stretched out thing where the electrons are not really close to either orbital, and it makes them really unstable. Once this intermediate forms, still relatively high in energy, then the chlorine can come in. Why can't the chlorine come in right away? There's too much sterics. These methyl groups create too much electron density, blocking the chlorine from coming in where it needs to come in to push out the bromine. So this reaction can't happen in one step. We're going to talk way more about this in detail later. When the bromine leaves and the carbocation forms, now there's an empty p orbital. It's flat. So the bromine, or the chlorine, can come in and start to bring its electrons into that orbital and start to share and make a new bond. During that moment of sharing, we'll call that number 2, that is going to be the time when the chlorine starts to bring its electrons in. During the collision, though, they're in no man's land. They're not really shared tightly between the nuclei or either on either one of the nuclei. And so the chlorine is starting to lose its negative as it's starting to share those in, and the carbon's positive is starting to be stabilized. So in terms of the charge, it looks more stable than the intermediate. But in terms of the electrons, when they're not held closely to either nuclei, it's an unstable point, and that's a transition state. But once that bond is secured, it'll take almost zero time, because once we get to this point, the electrons will get sucked into the sigma bond between the nuclei, and the optimal distance will quickly be achieved between those atoms, and that will be the production of the products. So make sure you understand an intermediate has the electrons in orbitals, and that means it's more stable than the transition states where the electrons are in the process of breaking or forming bonds, and they're very unstable because they're not in proper orbitals. The Hammond postulate is a little bit abstract, so we'll talk about that later in the context of some specific examples, so I'm going to skip over the Hammond postulate discussion. Let's talk about a reaction coordinate diagram. So a reaction coordinate diagram is one where I'm plotting the free energy versus the reaction progress. So it's just like these types of diagrams. I've got free energy on the y-axis, reaction progress or reaction coordinate on the x-axis. Oops, and I always have the reactants on the left and the products on the right. We're thinking about the reaction in the forward direction. So let's see, this example gives us some information. It says we want to draw a reaction coordinate diagram for a generic exergonic reaction. What does exergonic mean? Exergonic means delta G is negative, or that the free energy quantity is decreasing. So that tells me that the products are lower in free energy than the reactants. It doesn't tell me how much. We're not working with specific numbers, but just generically, I know they're less than the reactants if it's exergonic. If it were endergonic, it would be the opposite. So we'll look at that here in a minute. So if we have an exergonic reaction, and this is my mechanism, I've got a two-step process. So I've already labeled the axes. I got free energy on the y-axis, reaction progress on the x-axis. My reactants are A and D. This is the net reaction. A and D are my reactants. B and E are my products. But notice the mechanism. The mechanism shows me that A is reacting first. So A has to be colliding with enough energy to produce B and C. Once that occurs, that's an intermediate. And then the other reactant D will come in and collide with C, and that collision will also produce a moment where the electrons are not in proper orbitals, and then that will give me the products. So this is basically just to help you recognize that the number of steps in a mechanism can be translated into the number of transition states in a reaction coordinate diagram. So the intermediate here What's the intermediate? The intermediate is something that's formed in one step and then goes away in the second step. The intermediate does not appear in the net reaction because it's formed and then it goes away. It cancels itself out. So here the intermediate is C. And that's here at this point. The transition states are at the tops of the peaks. So this would be transition state 1 and this would be transition state 2. That's the moment where the electrons are in the process of breaking and forming their bonds, where it's most unstable or highest in free energy. If it were an endergonic reaction, the only difference would be the reactants would be starting at a lower energy than the products. So exergonic is where I start at a higher energy and go to a lower energy. And that gives me a negative delta G. Endergonic is where I start at a lower energy and go to a higher energy. That gives me a positive value for delta G. And so this is like the basics. We're going to use this to look at a lot of specific reactions, and we're going to be referring to reaction coordinate diagrams a lot. So just make sure that you practice up on this stuff so that you'll do well on the next exam, as well as allow yourself to start to understand the basics here so that we can build on that when we're looking at specific reactions. So that was a lot. I mean, a lot of it is review from Gen Chem 2, so we had to jam it all in there pretty much. But start practicing these sooner rather than later. And there's a few good questions from the textbook I recommend you practice to help you with those bullet points. And then on Tuesday, we're going to continue here with Chapter 6, and we're going to start to look at some specific examples of molecules that start to collide and form new bonds, and we're going to look at the mechanisms involved, and we're going to get back into arrow pushing, so that means there's going to be more assignments in the mechanisms app. And we're going to talk about curved arrows to show electron movement in other reactions, right? We've already talked about curved arrows in acid-base reactions, and we're going to start to talk about other types of reactions in more detail as well. So check that out in preparation, as well as obviously the quiz that's due for day 13 for next Tuesday. Any questions about anything? It couldn't hurt to bring a calculator, Amy. That's a great question. Usually the questions I give don't involve numbers. They mostly just involve positive and negative signs for delta H and delta S and delta G, and you work with the signs to make some conclusions, qualitative conclusions rather than quantitative conclusions, but you might want to bring a calculator just in case. And if there are examples in the textbook that I have assigned for you to practice that involve quantitative measurements or numbers, that would also be more of a signal that you might have to deal with something like that on the exam. But typically it's more conceptual than mathematical. Any other questions about anything? All right, well, I'm going to end the stream. And if you do have any questions, feel free to speak up or type them in there.